Hi, my name is Emily Dill. I'm a junior at the Institute of Optics, and the title of my poster is Requirements for a Simulated Photon-Photon Scattering Experiment, Sensitivity Studies and Absolute Vacuum Generation. So basically, my experiment is on photon-photon scattering. Basically, quantum electrodynamic theory states that we can have photons exchange energy and momentum through virtual electron-positron fluctuations um, in the vacuum. This is extremely rare. We have a cross section of 10 to the negative 66 centimeters squared. So if you had a dart and you were throwing it at a dartboard, that dartboard would be 10 to the negative 66 centimeters squared. Um, so in, in order for this to happen, we need this to scale with the power of the laser and the frequency of the laser. At the LLE right now, we're building the NSF Opal, which will output two 25 petawatt beam lines. And this is enough power to sort of get to the regime that we're looking for. So the experimental setup, once this laser is built, is we're going to have three laser beams, 1, 2, 3, and they're going to have this scattering be simulated in a known fourth direction. We'll put a detector at that place, and then we'll be able to measure the scattered photons. Since we can measure those, we'll know that we have virtual electron-positron pairs, and therefore sort of prove quantum electrodynamic theory, which is actually really cool. My job was basically to look into the mistiming and mispointing of the lasers uh, through simulations integrating over the Euler-Heisenberg Lagrangian, which is just an integral that explains the scattering over frequency and direction. And basically, um, we wanted to see how mistimed and how mispointed these lasers could be so that we could still do the experiment, have it be feasible, but also get a measured signal. So basically, we found that relative beam timing should be within the half width, half max of the pulse duration. And we also found that the beam mispointing should be within the smallest beam radius um, for all of the lasers. The second part is high voltage vacuum sweeping. Basically, the biggest contributor to the background is the ambient particles that are in the interaction region. So even one of these particles will completely almost destroy the signal, and we won't be able to measure anything relevant out of this. So our scheme to have zero particles in the interaction region over the time we want is to have two capacitor plates. We pump everything down to vacuum and shoot an ionizing laser through the center. This ionizes the leftover molecules and sweeps them out, and the ambient particles refilling happens on a much slower scale than that sweeping. So then we can have a period where there's no particles and we can get a measurable signal. So that's my poster.